Okay, dear participant, welcome to fourth International Symposium on Multidisciplinary Studies and Innovative Technologies. So we organized this conference online this year due to the Corona-19 virus occupying the world urgently. I hope you will get through this process without any trouble. My name is Mehmet Emir Köksal. I have been working for the Department of Mathematics of 19 Mayıs University located in Samsun, a city in the Black Sea part of the Turkey. Now we have 8 presentations in this session, but Iron, welcome again. Iron, just
Hi, welcome.
the speaker of the fourth presentation and the sixth presentation exists right now. So as a first, I invite Dr. Iron for presentation. The duration of each presentation is 15 minutes. Please pay attention to the duration of the presentation because there's also another session after this session. So I'm also chair of another session. Ahmet. Iron, so you can start your presentation.
Okay, so shall I start?
Yes.
Okay. So I'll just be sharing my screen.
Yes, sure.
Can you all see my screen?
Right.
Okay. Bismillahirrahmanirrahim. My name is Eri Amir Jalal, and today I will be presenting the paper of facial recognition-based attendance system using CNN and Raspberry Pi on behalf of all of the co-authors and the author. Now, these are the list of the items which I will be discussing throughout the presentation. A brief introduction to the problem statement is that attendance systems are usually managed manually in most of the educational institutes, and it is therefore a very time-consuming and a tedious job for teachers to maintain the records of the students. And if you can see that roll calling alone, it takes a significant amount of time from each of the class, therefore results in the loss of precious time which teachers have planned in order to share the valuable information with the students. So we have basically come up with the idea of facial recognition system, and for that the dataset which we have used for our paper is the DSU dataset. This dataset is generated locally at DHS Safa University, Karachi, Pakistan. The face images which we have gathered are of greater pose, expression, illumination variations, and all rights are reserved. So basically, we have generated 500 images, a total of 500 images of basically 5 persons with 100 images per person. So moving on to the details of the data set, it can be seen that these are the 5 people who have contributed to the facial database, and we have used 500 images for the training purpose, and for testing we are basically testing it with 2 different pictures which are basically group images as well as individual images. So for group images we have taken 39 group photos, and for individual images we have taken 150 individual images for the testing purpose. This is a sample of our DSU dataset, and as it can be seen that these are the 5 people which contributed. Their names have been mentioned over here as well. This is a sample of our test dataset, and as I was already talking about the group and the individuals, this is basically the difference between the group and the individual test images. For group images, it can be seen that it is basically a group of people in the image, and for individual, we are just having individual people. Now moving on to the face recognition algorithm. I'll quickly go through with the workflow. We have used convolutional neural network for the face recognition algorithm. Firstly, what happens is you basically acquire a face image. After acquisition, we basically perform face detection using hog or histogram of oriented gradients on the face on the image. This basically allows us to extract the face images out of the entire image. That is, create a bounding box around the face image. After creating a bounding box, basically we take those face images and we generate 128D embeddings of those face images. Now, what are the 128D embeddings? They are nothing. They are simply 128 real value numbers, which basically quantify the face image. After that, the training is done using the triplet loss function. I will be explaining this function in the next slide. For classification, we are using KNN model classification along with the maximum word counts in order to get a correct, in order to increase the chances of face recognition. The KNN model classification is already known. It basically works on Euclidean distance classification. That is basically calculating the Euclidean distance between the test and the training and working on that for the classification purpose. After getting the recognized faces, the faces are the attendance of the students is marked, and in a more efficient manner, we have also incorporated the addition of digital attendance management, which is through emails. So we are also sending emails to the students which are present in the class. So this is basically a 128D embeddings of an image. As it can be seen, this is simply a list of real valued numbers, which basically quantifies this image in this image in the face dataset. Now we are basically using two main libraries for our face recognition. One is the face recognition itself, and other is the DLib library. The DLib library is very important for the construction of the face embeddings, and the face recognition simply supports this DLib library. As for the triplet loss function, the triplet loss function works in a manner of tweaking the weights of the neural net so that the distance, the Euclidean distance between the anchor, in our case it is this image, and the positive, it tends to decrease, and the Euclidean distance between the anchor and the negative tends to increase. So this is basically how the training works, that it basically, the similar person, the distance between the images of the similar person is decreasing, whereas the distance between the images of different persons is increasing. Moving on to the experimental results of the DSU database. Now looking forward to this graph, it can be seen that we are just varying a tolerance parameter over here, and varying the tolerance parameter results in different percentages of recognition results. So it can be seen that 0.4 is by far the best parameter, which results in a fairly increased amount of recognition efficiency. And decreasing it beyond a certain value results in a decrease in the efficiency, and also increasing it beyond a certain value tends to do the same. From the images, it can be seen that a tolerance parameter is 0. We are getting all the unknowns, which means decreasing it beyond the optimum results in the generation of false negatives or incorrect rejections. So basically, people which are already present in the data set are also being rejected. They are not being recognized correctly. Now, increasing it to 0.4 results in correct recognition for the people which are present in the training data set, and others which were not present are marked as unknowns. So it can be seen that our algorithm is successfully rejecting people which were not present in the data set. And increasing it to 1 further results in the false positives, which is incorrect recognitions, incorrect matches. So people which were not present in the data set or which were present in the data set, they are all being recognized as the same person. So this is basically basically the disadvantage or the drawback of increasing the tolerance beyond a certain value. Now, as I've already told you, we have performed tests against group test images as well as individual test images. So for the group test images, we have already seen the results. Similar evaluation was made using individual test images. So these are basically individual pictures, and it can be seen that at tolerance 0, we are getting all the false negatives, that is all the unknowns for the people which are present in the data set. For tolerance 0.5, we are getting correct recognition results, and increasing it to 1 is causing the generation of false positives, which is incorrect matches. So basically, all the people are incorrectly matched. In the end, we have basically implemented the algorithm on Raspberry Pi, and emails are being delivered to the students using the SMTP protocol, or Simple Mail Transfer Protocol. So a similar evaluation can be seen that these people were present in the dataset and are also present in the image, so they are being correctly recognized, this, and this person. And it can be seen if you slightly zoom in that there are these 3 people are present in the email as well of the correctly recognized people. Similarly, it can be seen that for this image, this person, and these 3 are correctly recognized, and their names are included in the emails as well. So we are getting correct recognition results, and we are correctly sending emails to students as well. So this is a complete success at this point. So concluding what I've already just gone through is that we have successfully implemented the algorithm and tested it against a varying dataset. The dataset was very much varying. It had a lot of illumination variation, pose variation. It was not comprising of certain parameters. It was just a variation of all the things. And encouraging classifier performance was seen through by varying the value of the threshold or the tolerance. And majority of the images which were not present in the face image, or which did not which were not present in the training data set, were successfully rejected. So this is also a great achievement. In the end, I'd just like to acknowledge the Department of Electrical Engineering, DHS of our university, for their constant support in the regard of our research purpose. And I'd also like to thank all the DHS of our university volunteers for providing us with their biometrics and permitting us to use it for research purpose. So this is all from my side. Thank you so much.
Thank you very much for your presentation.
Thank you, sir.
Is there any question, comments, or remark? No question. Thanks again for your presentation.
Thank you, sir.
I think the speakers of the first 3 presentations do not exist. Now the next presentation is on the green coexistence of CP, OFDM, and UFMC waveform for 5G and beyond systems. The presentation will be given Mr. Ahmet Hamadi.
Yes.
Okay.
Thanks. Okay, can I share my screen now?
Sure.
Okay, thank you. Okay. Okay. It's clear?
Yes, sure.
Hello everybody, I'm Ahmed Hamoudi. Today I would like to present the green coexistence of the CBODM and University UFMC waveform for the 5G and beyond. This work has been done with the cooperating with the have listed in this presentation. I am from Wireless and Radio Sensor Center, University for Tun Hussein in Malaysia. The outline for this presentation: motivation, why coexistence waveform, why not conventional of DM-based waveform system model, non-standalone technology 5G and 4G, and the numerical and simulation result, and conclusion. Finally, the conclusion and future work. Motivation. Nowadays, today, the dynamic spectrum sharing technology allow for the dynamic change for the spectrum resources. As you know, today there are so many companies like a vendor and operator would like to use the dynamic spectrum sharing, the 4G and 5G, to share the same band, but needed to a good quality for the waveforms to flexible waveforms that to cover all the requirement for the 5G, as well as to achieve the channel performance condition. Therefore, the waveforms as a main part for the air interface and the wireless communication must be designed to achieve a high demand flexibility. The universal filter multi-carrier has one of the waveforms that the 3GPP standards to improve the spectrum localization and offer more robustness against and-time synchronization, as well as more suitable compared to the traditional OFDM waveforms. Study this combining affecting between the UFMC and the CBOFDM waveform is an interesting direct to access the coexistence effect on the overall the performance of the system with the different normology. Mean the different normology, it means that using the different spacing between the subcarrier. The Y coexistence waveform, non-standalone technology has been proposed as you see in the 3GPP release 50. Both the 5G and 4G will need it to deployment the same overlapping spectrum. One possible solution to have a abstract partitioning between the technology as shown in the figure below, it means that there should be the 4G as a LTE work with the 5G at the same spectrum. As you know, the company, the operator and the vendor spend $1 million today for the spectrum, and now they needed to use the 4G and 5G at the same spectrum as well as to reduce the guard band. But the main problem in these techniques, you should be use the a smart a smart waveform that to reduce the out of band emission, where asynchronous normology with the different subcarrier spacing, power level, and the using case several requirements operating in the same network in the 5G network with a different waveform. In such systems, each normology should be serviced several synchronized devices and access to the different band part. Uh, why not conventional OFDM? OFDM have some limitation. The first of the limitation is high out of band emission. Due to using the rectangular window after the off of T, the OFDM has a leak from the out of band emission. It means that the interference to the other band. The second limitation, high peak to average power ratio. It means that the amplifier will be not work with the linear region. It's more also the sensitive to the carrier frequency offset, as well as the Doppler shifting. The last limitation, the CPO of DM use the cyclic prefix. This is the effect for the efficient for the spectrum. It means that will be lose the spectrum. The coexistence waveform problem, when we use the CBOFDM as a 4G system with the 5G system, UFMC will be interfere to the universal. It means that the out of band emission is the demand of the one most of the critical challenge in the coexistence in different normology that have to be properly addressed in order to guarantee the success deployment for the future technologies such as 6G and beyond. Also, the coexistence 5G should be designed as orthogonal or quasi-orthogonal as possible with the respect to the 4G waveforms to affect the minimum the mutual interference. And now, in the next slide, the system model that will be designed in this paper will be used the CPOFDM as a 4G and will be used the UFMC as a 5G system, but not use the traditional or conventional, as I mentioned in the previous slides, using the rectangular window. No, will be used the Kaiser window. The Kaiser window have a controller to reduce the out of band emission emission when we coexist with another waveform like universal multi-carrier waveforms. This is the structure for the universal multi-carrier. Will be divide all the subband to the different subband and filter each subband to reduce the out-of-band emission. This is the addition benefits that can be used to success the coexistence in the 5G and 4G system. The system model will be used the different spacing, carrier spacing. It means that different normology. 15 kilohertz will be used in the 4G, and the 30 will be used in the 5G. This is the numerical and simulation result. This is the CPU of FDM and universal filter coexist as a same band with the same waveform. This is the simulation parameter will be put in the environment, the 5G system. It means the environment for the 5G system, all the requirement, the 5G, and this is the combining between the two waveforms. It means that they're using the UFMC and 4G system are the same band. As you know, today have many problems that will be faced with the operator and the vendor to use the 4G and 5G coexist with the same band. This is the simulation using in MATLAB, as well as using the numerical result evaluation by cooperate with the Nokia team to evaluate my system. This is the main simulation parameters. They are using the FR1. It means that the 15 and 30 as a space for the frequency cyclic channel will universal, as well as I will use the multi-window like Kaiser window to reduce the out-of-band emission. The simulation result now to show the Kaiser window have a control by using beta function and well as using the Hankel function to reduce the out-of-band emission. It's clear that when we increase the beta, it means that it will be reduce the out-of-band emission. This is the power spectrum density for the conventional UFMC by using the Chivy filter. After using the Kaiser window and coexist with the CPU FDM, it's clear that the out-of-band emission is decreasing. As well as it could be clear that could no interfere between the different band. The 3GPP standard have give us the limitation for the out-of-band emission. Now it's clear that the system will be correct successfully after the 100 dB. The next slide, this is the green coexistence CPU of DM by using Kaiser window, by using generation and the NI. The bit error rate for using the 64 Quam Kaiser universal filter multi-carry and the CPU of DM after the signal to noise ratio at the 6, it means that all the system equal the bit error rate, but after that will be the CBO FDM is better than the UFMC. This is the conclusion and the future work. This paper suggests a new design for the coexistence for 5G LTE and the 5G system while reducing the out-of-band emission, the bit error rate, and improving the BSD. Several window and the filtering method were tested, and the results show a great improvement over the CBO FDM, a huge reduction in the OOP emission pattern BSD, and compatible with the bit error rate as a lower signal to noise ratio region are only some of the advantage of the suggesting waveform in this paper. The direction for the future work include improving the bit error rate further for the large signal to noise ratio value, and taking a new flexibility demand in consideration when designing the more adaptive and the flexible waveform. Thank you. Any questions?
Thank you very much for your presentation. Is there any question, comments, or remark? No question. Thanks again for your presentation.
Thank you.
Next presentation will be given by Mr. Ala, and title of the talk is Localization of Mobile Robots Through Reference Point and Target Positioning.
Thank you, sir. Good morning, everyone. Yes, sir.
Yes. Okay.
Should I start?
You can start.
Okay. Good morning,
We can-
everyone. My name is Ala Al-Dhafari. I'm working alongside with my colleagues Abdullah Ismail and Nurullah Akaya. We are master students in the Department of Computer Engineering, Near East University, Turkish Republic of Northern Cyprus. And today I'm going to be presenting our work on behalf of my colleagues, the localization of mobile robots through reference point and target positioning. In this presentation, we're going to go through a few points: the introduction, the aims and objectives of our studies, the method we developed, and our results, limitations, and we get to the conclusion. So, as an introduction, first we have to discuss the localization and navigation of the of the mobile robots. So, the localization is the ability of the robot to determine where it is at every second. So, like, meaning it should realize its location. And the robot navigation is the ability to determine actually the path and go through some of certain path. In this work, we try to present a low cost algorithm for localization and navigation that is effective in both indoors and outdoors, alongside with being easy and simple to implement. The reason is normally the localization or navigation is not the main task of the robot, and if we want to implement any other navigation or localization algorithm, it will consume a lot of the processing power on the expense of the main task. In this work, we demonstrated our algorithm is through a target or object finding robot. Sorry. Previous works had different methodologies on this. For example, one of them, or like a lot of them, actually uses vision-based system. For example, the visual simultaneous localization and mapping. Others are using sensors like ultrasonic and encoders and mobile applications. Some of them were hybrid, where they used camera and sensors combination to determine the localization, the location of the robot. For our research, we use only sensors, and like they're pretty simple sensors, which are the motor encoder and the MPU, which is a gyroscope and accelerometer, to determine at every minute where the robot is, the location of the robot, and as well as the orientation of the robot. Our aims and goals were to generate an algorithm that is generic for indoors and outdoors, since a lot of other work is restricted to this kind of stuff. So it may be an indoor algorithm or an outdoor algorithm, and maybe limited to a small area. So we try to generalize this. Again, our aim was to be low cost, both financially and in the means of processing powers. We developed a simple object robot reference system for the robot to understand the objects around it and how to reach it using the same simple method. As I said, the algorithm was tested on an object finder robot. So therefore, we have the visioning system in our work later on. So the method actually consists of three main parts: the visioning, the obstacles avoidance, and the localization. The visioning was used to identify the object when seen. The obstacles avoidance to make sure that the robot goes through a safe path and do not collide with any dangers or big obstacles. and the main point, which is the localization. For our visioning system, we actually used a customized version of YOLO, you only look once, which is a well-known object recognition algorithm. We modified it to where we attached the camera to a servo motor, and we linked each degree or each few degrees of the motor to a frame, while of course ignoring the same frame. If the frame repeats, that's why it does not even like the accuracy of the servo motor does not affect the work of the algorithm. We use the all the frames that the object appears in, and then select the middle frame of them to determine where the object is in reference to the robot. As for the obstacles avoidance, we considered three cases, and to achieve these three cases, we used simple ultrasonic sensors are placed in front of the robot, high enough to detect the objects that are large enough that the robot cannot override. To override the small obstacles, we use the chain design for the robot. So any small obstacles, it can just override it. Anything larger than this should be detected by these 5 ultrasonic sensors. And the cases we discussed in this obstacles avoidance is small obstacles, which are like, for example, a small table or a can, maybe. In this situation, the robot is just gonna overtake it from one of the safe sides. So, like it uses the side sensors to detect which one is the safe side and goes through it. The large unmovable obstacles, for example, a wall, then when it faces a wall, it should, these sensors, these side sensors are used to detect the safe path and redirect the robot towards it. And the dead end is actually detected through 3 sensors, the middle sensor here and one of like and 2 of the side sensors. Either these 2 or those 2 depends on the speed of the robot. Once all 3 sensors are blocked, we know that it's a dead end and it has a handling method there. For our localization method, we got inspired by the breadth first search algorithm, since this is a search algorithm that is used in the tree structure in computer science. If we take a look to the chart on the right, we assume that the environment looks something like the tree structure. In this area here, we have each level has an index, which is the number of steps taken by the robot from the initial point to this index, to this level, and each node is defined by 2 parameters: the index and the angle, which is the angle in reference to the initial angle. The initial point is always considered to be 0 of index and 0 of angles. So by considering this, we can see that this is 1 minus 90 degrees, 1 minus 45, 1 0 degrees, and so on. We move on to 2. This gives us unlimited number of nodes and unlimited number of depth indexes. Our formula is basically the step, which is how many centimeters or how many meters, so the step value times the index, and with the consideration of the angle. So this is how we detect where the position of the robot. In the return journey, since we went through a safe path, we want the robot to take the safe path again, because we don't know anything around it, and we don't want to rediscover the environment again. Therefore, every step that the robot takes, whether it's a step or a turn, is stacked in 2 stacks. One is for the indexes or the steps, number of steps, and one is for the turning. So basically, if the robot moves 3 steps, it stacks 3, and then it turns, for example, 45 degrees, it will stack 45 in the angles stack. And when we want to perform a return, we pop these values in reverse. So we turn and then move 3 steps again. And since our object may be found in somewhere in the middle of 2 indexes or in the middle of 2 sharp steps, we use an accumulator to overcome this issue by recording the value of this encoder as long as the robot is going until it reaches the other index where it will be reset to 0 again. This is a flow chart, a simple flow chart of the entire localization. So it tries to move until the encoder detects the distance of the distance that is predefined by the omega value, records the depth index, and check for targets. If the target is not found, it will move again. Once the target is found, it will turn towards the target and, of course, stack the angle that it turned and start to move towards it. Once the target is in hand, we should check if we moved a sharp step, which is like a full distance, or not. If not, we accumulate the distance that we've passed, and so that when we turn around, we want to move this number that is saved in the accumulator, and then start to pop the indexes of the distance again. If it's a sharp step, we count the depth and set the accumulator back to 0. Now, once we have the target in our hand, we catch it and like turn around 180 degrees and start the move back procedure, which is actually just popping out the values. First of all, running the accumulator till it's 0, and then popping out the values from the stacks. In order for us to determine the position of the robot or the location of the robot at any time, we can use simple vectors addition. So if by just looking through the data that came from the sensors that are stored in the stacks. For example, in here we can see that it moved 3 omegas, then turned 60 degrees, then 2 omegas, then minus 45 degrees, omega 30 degrees, omega. These values are all stored in the stack. So by just looking at them and taking one at a time, we can perform some simple vectors addition, and we get to know that the robot is here in relation to the initial point. The results in this section, we are going to present the result of the trial distances, the trials on finding the target, and the errors in values on our way back. In this work, based on our design and our environment, we assumed the value of step to be 10 centimeters, which is our assumption. It will be different for each application and each design. But the initial point is always considered to be, as I said, 0 point and 0 degrees. For the first table, we can check the number of the errors in the steps passed with the robot while it's going through the trip. So in here we can find that the errors, the robot actually did not move at 10 centimeters sharp, and that is due to few reasons. One of them is the mechanical delay. As the robot gives, like if the controller gives the command of stopping, it will take few time for the robot to, or for the motors to actually stop because of the mechanical delay. And the speed of the robot, the faster the robot goes, the more the mechanical delay will affect the stopping procedure. But with this being said, the error values are still in the accepted ranges. For example, like the maximum value we had was 0.31 centimeters, which is like 3 millimeters. So it's still accepted in compared to 10 centimeters. The second table shows the errors in the angles after finding the target. So before finding the target, our target angle stays as 0, and we don't have any turning, so no drifting. There will be a PID to we use the PID to maintain the robot on track on a straight line. However, the PID still have some errors, and these errors comes from different motors alongside with the errors coming from the MPU itself. But as you can notice, it's very little that we can ignore it actually. On step 4, the target was found and the robot is going to turn 60 degrees. Now in here, turning requires more power, or as our robot and our design and environment, it required more power from us to deliver a turn, and therefore it results a more than 60-degree turning. So we drifted by around 75.5 degrees. But then after we moved this step number 4, we reduced that error back to 4, which is controlled through the PID. And with the 5th step, the error reduced again and again until we reach a value in between 0.7 and 1.2. Now this table represents the errors and values on the trip back to the initial point. So first of all, the turning around, we use a different technique for turning around than the one used in just turning towards the target. Therefore, it reduced a smaller error in the end. Now, on the way back, the robot actually performed a slight error in the distance passed. Instead of 65, sometimes it gave us 63, 62, and sometimes it gave us 67. So it may cross beyond or after or before. In the turning back, when we were turning back, the average of the error was reduced to 1 degree. Since we use the same technique that is used in the turning around this time around. The drift from the 0 point, since the initial point is at 0 degree, so we try to maintain this at 0 degree, but again, due to the different mechanical parameters of the motors and the MPU errors, that results some errors as always, and we try to maintain it by tuning our PID. We ended up with plus minus 2 degrees alongside along the way back. And at the very end point, instead of, sometimes we stopped at 0, sometimes more, sometimes less. That is again due to a lot of factors: the motors, the battery, and the surface underneath the robot. Our limitations were, since this is going to be a mobile robot and it has it has to find a target, so this should be a completely autonomous robot. And our first challenge was actually to find a mobile platform that is capable of performing the visioning system that we seek. And then we have the battery limitation. For example, if the target was far away, really far away, then the battery may run out before the robot can detect where it is. Then we have the encoder accuracy, which affects the number of steps that we take. Sorry, not the number of steps, the values of steps that we take, because the less the accurate the encoder, the more the error we end up with. And of course, we have the environment. Like if it's by environment, we are talking about the surface that the robot is surfing over. The harder the surface, the more friction it results, the more power it consumes, the less speed it goes and less errors it goes, and so on. Magnetic fields, if the robot passes through any magnetic fields, this affects the MPU, since the MPU is affected by a magnetic field and results some random and mistaken values. In conclusion, in this work, we have presented a low-cost algorithm, both in terms of finance and processing expenses. It's effective for both indoors and outdoors, since it does not rely on any cameras or visioning system or predefined areas. It performs a blind search in an unknown environment. The sensors that are used in this work were the MPU and an encoder, which are used to detect the location of the robot at every time unit. The object recognition used to find the object is used to it used to give the robot or the angle or the location of the object in relation to the robot at that time. The custom designed obstacles avoidance is implemented. We used breadth first search, assuming that the environment looks like a tree structure. Our work demonstrated 10 centimeter steps value, which gave us the most, it was the furthest distance we could go with the most accurate results. Of course, the faster the robot goes, the more a lot of factors will affect the process and the motion of the robot. Therefore, it's for our work, it was better to not go with full power. We used half power and we used full power when it's needed to turn the robot. That would be it for our work. Thank you for listening.
Thank you for your presentation. Is there any question, comments, remarks? No question. Thanks again for your presentation.
Thank you, sir.
So unfortunately, speakers of the other presentations do not exist. So we end up this session. I hope we meet in another international conference face to face. Thanks for your participation to this session on international conference. You can get all video records from the web page of the conference after the conference. It's tomorrow or in the next 2 days.
Okay.
Thank you, sir.
Okay.
Thank you.
Okay. Nice to meet
Thank
you
you.
again.
Thank you.
Thank you, sir.